Problem number 54 from our optimization section. It's 4.6 in our textbook. It's the Stewart Kokoska edition 1 AP calculus for AP students. We're trying to make an optimal cone-shaped drinking cup from a circular sector. And this is really a general problem here. We've got an unspecified constant radius for that sector. We're calling it big R. So it's like you have a circle, and we're going to basically cut a wedge out of the circle to not use, so we can fold the circle up to make a cone. If you're actually doing this, if you want to make one for a model, don't cut the wedge out. Just cut a slit right here, and you can kind of slide the paper over on itself. And it's like removing the wedge, but then it'll actually like tape or glue to itself, and it's actually stronger. Anyway, so one way to think of this, we could use a central angle here of theta, which would represent our main variable then, because you can get the radius and height of the cone in terms of theta. But honestly, and I wrote that here, the true variable is theta, but I think we can do this problem without really getting into theta. So I'm going to show this. I've got the that sector there with the theta identified. And then here's my cone. I'll just put it on there. In my cone, big R, that radius of the sector, is the slant height of the cone, right? If you picture folding that paper up, putting the edge there to the edge there, then that R is going right up the slope of the outside of that cup. So big R is a constant. Keep that in mind. Little r and then h, those are variables. They're dependent on whatever angle I choose there, what the theta that I'm going to use, right? Whatever that is. And that's really, that's the question, like how much of this circle is getting cut out to make the cone. But even though theta is kind of like the main variable that way, even though r and h can be expressed in terms of theta, I don't know that we necessarily need to use theta to solve this problem. So let's start with our primary equation, the volume of the cone. And the volume formula I know for cone is, 1/3 pi r squared h, right? 1/3 of the area of the base of the cone times the height of the cone. So here, I really just need to relate. Our goal with optimization problems is usually to have this primary equation, the thing I'm trying to maximize or minimize, in this case, maximize volume. You try to have it in terms of one variable, but right now I have two variables. So what I'm going to do is do a substitution to turn either r into h or h into r, right? That's my goal here. So here's my relationship right here. I'm going to relate them both to big R. And so I have Pythagorean theorem, right? Because that's a right triangle. So r squared plus h squared equals big R squared. And by the way, if you're at a point now where maybe you didn't know where to start this problem, but you're watching and now you've got an idea, you should pause the video and try to do it yourself, and then kind of see if you can skip around then and see if you match it up or see if you get stuck again. Anyway, this is a secondary equation right here, right? This relates r squared and h squared, like little r squared and h squared, which I can now use to, I can use that equation to get rid of one of these variables, right? In the primary equation. So that's what I want to figure out is the best way to do that. This is a secondary equation. This is my primary equation. The reason that this is the primary equation up here, the volume equation, this is the thing I'm trying to optimize. Instead of writing, I was about to write thing to be maximized, but I'm just going to say maximize volume. Maximize, that's my goal, right? So you can, annotate your work this way too if it helps you. The secondary equation, any secondary equation, usually the purpose is to eliminate a variable in your primary equation. And I have choices now. I can either solve for h down here and substitute in for h there, or I could solve for r, or better yet, I could even solve for r squared, because I have r squared right there. And that is really useful. If I solve for h down here, there's going to be a square root in it, right? It's going to be the square root of big R squared minus little r squared, and that's annoying. So instead of that, this problem gets a lot easier if I say r squared, little r squared, equals big R squared. Remember, that's a constant, minus h squared. And I can just plug that in now for the little r squared. So I'll keep the red, I guess. So v is equal to pi over 3 times big R squared minus h squared times h. Oops. And I'm going to go ahead and just work with that now. Pi is a constant, big R is a constant. The only variable now over here is h. So that's good. That's what we're going to do. But I'm not going to differentiate just yet. There'd be a product rule right now. That's annoying. So let's just make this um, pi big R squared over 3 times h, right? I'm distributing, minus pi over 3 times h cubed. So again, I'm distributing both the pi over 3 and the h to both of these things inside. Okay? And so now that's v. And once you have v in terms of one variable and it's convenient to differentiate, we'll just go ahead and do that. So I can call this v prime of h, or I'll just say dv dh, use the Leibniz notation. And yeah, this is just a constant times h, right? So it's just going to be the constant pi big R squared over 3. And then this part, it's just the power rule, bring down the 3, cancels with the 3 down there, and I get pi h squared. And I want to take that derivative and set it equal to 0. Some people will go right into, they'll say, oh, equals 0. That's not really the best notation. Um, this is a nice clean version of dvdh. You should leave that alone. It's good work to have in your work. And now just say, okay, dv dh equals 0. That's like the work I'm doing next, right? And I'm going to do that now. I'm going to set this equal to 0. And when that's equal to 0, I would just add the negative term to the other side, right? So I'd get like pi big R squared over 3 equals pi h squared, right? So this is I'm setting this equal to 0, and this is my resulting equation from that. So like on the AP exam, that's what they're going to be looking for, right? If they're going to be looking for steps along the way, or in your calculus class, your calculus teacher, perhaps me, is looking for this clean derivative step, and they're looking for, are you setting the derivative equal to 0? Those are the things we want to see. And then, of course, go through and do the computations correctly. The pi's cancel out nicely. And we get h squared equals r squared over 3. What did the question ask for? The question asked for the maximum capacity, the maximum volume. So whatever we get for h, we're going to need to plug back in to our volume function. Okay, so just keep that in mind. So h is the square root of big R squared over 3. So it's big R over the square root of 3. We don't care about a negative square root because, we're dealing with measurements here. You're not going to have a negative height in our cone. So that's my optimal h. The optimal height of my cone is the the radius of the original sector divided by the square root of 3. And so what I'm going to do is plug that now into my volume formula to find my optimal volume. The optimal, I was going to write optimal, but let's say max, because that's what it is, right? It's the max volume. And it's going to be pi over 3 times big R squared, right? I'm looking at this term right here, times h. So that's times r over square root of 3 minus, now I need this term, pi over 3h cubed. And h cubed is r cubed over 3 square roots of 3, right? And so I want to put this together. I could factor out the pi over 3, and that leaves 1 over the square root of 3r cubed. I'm going to need another 3 in the denominator over here, so I'll just go ahead and do that right now. I'm going to have 3r cubed over 3 square roots of 3 minus, I took a pi over 3 out already, so that's just going to be 1r cubed over 3 square roots of 3. And so that simplifies to 2r cubed on top there. So it's 2 pi r cubed, if I put it together with the stuff out front, over 3 times 3 square roots of 3, which is 9 square roots of 3. I believe that's good. I don't think I did anything wrong there. So there's my max volume. So basically, if you take any circular sector, so you have a circle and you're going to cut a sector out of it or cut a slit in it to slide it around and make a cone out of it, that is your optimal volume. That's the most volume you could get from that circle. And it's in terms of big R, the radius of that circle you started with.